Hey everyone. So today we're going to be starting our first lesson of our unit on Newton's laws. So this is actually, I think, the best unit because we get to do the egg drop in this one. So obviously things are going to go a little bit differently since we are all at home, but I have a few good ideas up my sleeve that I think we can try out to still make this as fun, if not more fun, than it would be if we were in school. But before we actually get into the projects and all of our fun experiments and activities, we do need to learn the kind of science behind all of these fun things. And that deals with Newton's laws of motion. So we're going to be talking today about Newton's first law, the law of inertia. And then tomorrow we'll be doing the second law, force equals mass times acceleration. And then the day after that, we'll be doing the action reaction law, or the third law. So I kind of took what you guys said through the survey. I'm going to try and make these videos a little bit shorter. Of the 3 videos for Newton's laws, this one is going to be the longest because we have to go over balanced and unbalanced forces, which some of you may or may not have gotten in grades 3 and 4 and 5. So we're going to just kind of do a quick recap in terms of that. But let's get started. So Newton's laws of motion. Some of you may have heard these before. They're kind of like common knowledge sayings that you hear people talk about from time to time. But these are the 3 laws. So the first law says that an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by an unbalanced force. Second law says force equals mass times acceleration, so it's literally a equation. And then the third one says for every action there is an equal and opposite reaction. So we're going to be going through each one of these in a separate video, kind of in detail, and today's is going to be the first law. So before we can get even into those laws, this is kind of the recap section. So going over what you may have learned in grades 3, 4, 5 about forces, and kind of giving you background information so that you can take in the 3 laws and understand them actually. So remember that a force is a push or a pull that causes a change in the motion of an object. It's pretty much any type of cause for a change in motion. So it could be a literal push, like, your brother or sister pushes you, that could be a force, or it could be something that's a little harder to see. So these are examples of ones that are harder to see. For example, gravity. We know that when we drop a basketball, it's going to fall to the ground, but there is a force that's acting on that basketball. It's the force of gravity pulling it towards the center of the earth. Over here, we have this should look familiar. The Earth and the Moon. Gravity is the force that keeps the moon orbiting around Earth. It pulls it towards Earth. So there's that pull. Okay. We also have electricity, static electricity especially. Sometimes when your socks will stick to like a hoodie or whatever that was in your dryer, that is a good example of static electricity. It's a force that's pulling electrons closer together. Then we also have magnetism. We're pretty familiar with that one. Magnets, or things that are magnetic, will pull together. And again, that's that pull that will cause a change in motion. And then finally, friction is one that we don't necessarily think about too frequently. However, it is a force that will cause a change in motion. And pretty much it's the force that opposes motion. It is going to slow things down. So if you are playing basketball, you buy basketball shoes on purpose because they are designed to have the proper amount of friction against the floor. With a bike, when you are riding your bike, you apply the brakes, your wheel stops turning, it creates friction on the ground, and then it slows you down. So all of these are examples of forces that you may not necessarily think of immediately. Like we always think of a force as like a person touching something. But these are all forces that can affect motion as well, or cause a change in motion. All right, so another thing that's important to know about forces is that it is a vector, or we could say it's a measure that has size and direction. So, for example, if we take this kid who's on his little scooter, if he pushes on the ground, like with his back foot, he pushes, he's going to go forward, but his foot pushed backwards, right? That is the direction part of a force. So depending on how he pushes, he's either going to move forwards or he's going to move backwards. In this case, he pushed backwards, so he moves forwards. Whether we know he's going front, back, left, right, that's the direction piece of a force. The size is like the strength, okay? Did he kick off with a big push? Did he kick off with a little push? That is the size of the force. So any type of force that we're going to be looking at has both size and direction, and they are important. Later on, we'll see, even if an object changes its direction, it has changed its motion. So that's going to be important when we look at that later. So there we go. So any type of force that we see is going to have a size, meaning like it's going to be strong or weak, and it's also going to have a direction. Is it going forwards, backwards, left, right? That's going to come in handy when we look at some diagrams. And then here are the diagrams that we're going to look at. Basically, when we're looking at diagrams of forces and interactions between objects, typically when we look at these diagrams, we're going to be seeing lots of arrows. So with any vector that shows size and direction, the forces are going to be represented by an arrow. And basically, the length of each arrow is going to represent the strength of the force. So if it is a shorter arrow, it's going to be weaker. If it's a longer arrow, it's going to be stronger. Okay? So in this one, force A is a weaker force than force B, okay? Because B is a bigger arrow, but they are going in the same direction. Okay, so again, when we look at these arrows, we want to look at the size and the direction. They're going in the same direction, but B is a stronger force. In example 2, we're looking at the direction, and we notice that force A is going to the right, force B is going to the left. They're going in different directions, but now they're the same size. So that means that they're going to be the same strength of force, but they're going in opposite directions. So these arrows are going to be going to come in handy when we look at diagrams of different forces interacting on objects later on. But this is just kind of an overview of some important things that we need to know about forces so far. Okay, so again, to recap, forces are a push or a pull. They can be obvious forces, like if a person touches something, or it could be one of these kind of almost invisible forces that we don't necessarily see. As long as it pushes or pulls and causes a change or could cause a change, that's a force. We know that forces have both a size and a direction, meaning it depends on the strength of the force. When we are showing it in an arrow with an arrow, if it's a bigger force, it gets a bigger arrow, and the direction shows the direction of the force. Okay? All right, so this brings us to balanced versus unbalanced forces. And again, depending on where you guys kind of were at, some of you may have learned about this before, some of you may not have learned about this. But basically, a balanced force is when they are opposite in direction, but they're equal in strength. They will not cause a change in motion. Okay, so if we look over here, we have 2 arrows. One is going to the left, one is going to the right. So here we go. And if we look, they're about the same size. And this one's kind of easy because it gives you like a numerical value. It says 5n. 5n. We'll get to what the n means later. But basically, it's showing us that they are equal in size or strength, but they're going in opposite directions. So if there were, say, a box right over here, we would not have that box moving whatsoever because it's not going to the left, it's not going to the right. They're equal in size, they're not going to move, okay? So objects that are not moving will not start moving if acted upon by balanced forces. Okay? If it was already in motion, it's going to keep doing exactly what it was doing before any forces were applied to it. So that's balanced forces. Balanced forces are equal, no change. That's going to be important. All right, now unbalanced forces are unequal, and they will always cause a change in the motion of an object. Okay, if we look over here, we have two arrows. One is going to the right, one is going to the left. So now they are opposite, but they are unequal. Okay, this one, 10, is bigger than 5. So if this were a box sitting here, the 10 is going to win. The box is going to go to the left. Okay? Over here, if we have 5 newtons pulling to the left, 10 newtons pulling to the right, and a box is over here, 10 is going to win. It's a bigger number than 5. So now it's going to go to the right. Okay? So basically, in a balanced force, they're equal, no change in motion. In an unbalanced force, they are unequal, and there will be a change. Okay? We'll talk more about combining forces and kind of actually getting, but you can probably figure out with this image. We'll talk more about this right here, which is called net force when we get into the second law. Okay? But basically, all we need to know for now is that balanced forces are equal, no change in motion. Unbalanced forces are unequal, and there is a change. Okay, so here we are with our first law. Basically, it says an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by an unbalanced force. So basically what that means is if we have a box, it's going to stay still. Or let's say we had a car and it was moving. It's going to stay moving at the same speed. Velocity is just a fancy word for speed, unless acted upon by an unbalanced force. So unless there's a force that changes it, it's going to keep doing whatever it was doing. If it was staying still, great, it's going to keep staying still. If it was moving, it's going to keep moving, unless an unbalanced force acts upon it. So a force that is stronger on one side than the other. So let's see what inertia is. Because if you look, sometimes we call the first law of motion, its like nickname is the law of inertia. So we need to know what inertia is. And basically, it's the tendency of an object to resist changes in its velocity, whether it's in motion or motionless. So that's kind of exactly what the first law said. An object is not going to want to change whatever it is it's doing. It wants to resist a change in its velocity, whether it's sitting still or it's already moving. So if you've ever seen those challenges where you have like an egg on top of a plate and you got to get it into the cup of water beneath it, that is showing inertia. Same thing here. Basically, this coin was on top of the card, and if you flick out the card, the coin doesn't go with the card, it drops right into the cup. That's because the coin has inertia. The coin is resisting a change in its velocity. The reason why it kind of just fell is because it was resisting that change. Now you, or this person, imparted a force on the card, and the card started moving, but not necessarily the coin. Another thing, too, that is important when we learn about inertia is that inertia depends on the mass of an object. If an object has greater mass, it will also have greater inertia. So if you think about what is heavier, a coin or a little card, it's going to be the coin. So when you flick the card out, it's going to go woo, because it's not got a lot of inertia. It's easier to change its motion. But the heavier something is, the harder it is to change its motion. So the coin is going to be harder to change, and that's why it's just going to fall right into the cup. All right, so with the first law, again, it was an object at rest will stay at rest, an object in motion will stay in motion at a constant velocity unless acted upon by an unbalanced force. So, according to the first law, this golf ball is going to have inertia. It is going to resist changes, it's going to sit still, it's an object at rest, and it's going to stay at rest unless an unbalanced force hits it. So, unless acted upon by an unbalanced force, this golf ball would sit on the tee forever. Now, if it were to change its motion, inertia of the golf ball would have to be overcome by an unbalanced force acting upon it, like a golf club hitting the golf ball. Okay? So if you took your golf club and you actually hit it, that would be the unbalanced force to change its motion. So it was sitting still, you whack it with a golf club, you just gave it an unbalanced force to overcome its inertia of wanting to stay still. Okay, so that's kind of the first part. Now, the first law also says an object in motion will stay in motion at a constant velocity. So what that means is this golf ball, once you do whack it with the golf club, is going to stay in the air unless an unbalanced force stops it. So if there was no unbalanced force acting on the golf ball, it would never stop theoretically. But if you think about real life, there are forces that are acting on the golf ball. Basically, air is going to slow it down. There's friction between the air and the golf ball, so that would slow it down. There's also, it could hit a tree, it could hit a golf cart, who knows? But unless it's affected by an unbalanced force, it would never stop. Oh, gravity, that's a big one. Okay, gravity will pull it down. So that's another example of a force that could stop it. Okay, so again, once an object starts moving, inertia keeps it moving without any additional force being applied. Remember, inertia is the tendency of an object to resist a change. So once this golf ball is moving, inertia says you're going to stay moving. In order to overcome inertia, in order to stop the golf ball, an unbalanced force has to stop it. Okay, so again, forces that could oppose the golf ball's motion could be friction, could be gravity, could be a collision with a tree. You get the idea. All right, so then this goes over friction. And again, this is that unseen force that could cause a change in motion. Sometimes we see everyday objects in motion slowing down and becoming motionless without an outside force. So if you kick a soccer ball across the grass and it just stops moving, okay, it's likely due to friction from the grass. And basically, it's just a force that we can't see, and it opposes motion. It slows things down. When we think about objects on Earth, everything is under friction because there's air on Earth. So although, yay, we have air, we can breathe now, it is going to slow anything down that's moving, okay? Because guess what? Things move through the air, and good thing there's air, but it's going to slow things down. So objects in motion are always under the force of friction. So that's something to think about too. When we are thinking about different forces that are acting upon an object. If it's moving, there's friction by the air. All right, and finally, Newton's first law and car safety. Basically, engineers that work on cars and engineers that try and develop safety devices in cars use Newton's first law to help them. Okay, so again, remember, an object at rest stays at rest, but an object in motion will stay in motion. That could be a problem if you're the object in motion inside of a car and the car suddenly stops, but you don't. That's where we run into an issue. So, because of inertia, objects, like even humans, will resist changes in their motion. When a car is going 50 miles an hour and is stopped suddenly by your car's brakes, your body's going to keep moving at 50 miles an hour. If you've ever been in a car and it stops short and you kind of jolt forward, that is inertia. Okay, you are resisting a change. You were just going at 50 miles an hour, but now the car's brakes stopped the car or slowed down the car, but it didn't slow you down. So you're going to keep moving a little bit forward. That's why safety features like seat belts and airbags are designed to apply an unbalanced force to anyone that's inside the car. So if there is a sudden change in the motion, the car is going to be damaged, but not the person, because the seat belt is going to be the unbalanced force that stops them instead of the windshield or the dashboard or anything else that could be potentially dangerous. So thankfully for us, we kind of use Newton's first law to help us to stay safe. And that's pretty much it for Newton's first law. So big takeaways. Let's see what we have. But basically, our big takeaways are forces are a push or pull that causes a change in motion. Forces are a vector, meaning they have size and direction. And when we look at a example, and you'll see some later on in here, whenever it shows an arrow, the arrows really do mean something. The larger the arrow, the stronger the force. The arrow also points in the direction that it goes in. A balanced force is equal in strength, but it does not cause a change in motion. An unbalanced force is unequal in strength, and it will cause a change in motion. And then we have Newton's first law. Remember, inertia is the tendency of an object to resist changes. So it wants to stay if it was at rest, it wants to stay at rest. If it was in motion, it wants to stay in motion. And the only way that it's going to change is if it has an unbalanced force. So again, resting unless you hit it with a golf club. Then once it's going in the air, it wants to stay going in the air unless something stops it, like gravity or friction. Friction exists between anything that's moving on Earth because we have air. So good for us, but bad for moving objects. And finally, they use Newton's first law of inertia, to help us to stay safe in cars. So basically, we will go over the second law tomorrow. There are some videos at the bottom of some of these slides, and they kind of go over what they are. So you can feel free to watch these as kind of additional information. They may be helpful, especially if there's one part that you're not quite getting. And that's about it. Don't forget that you have an exit pass to finish up. And I will talk to you guys later.